This is the moment of inertia derivation for a solid sphere. Here you can see a sphere to your left of radius r and a disk within the sphere of radius y. The disk also has minimal thickness dz. So the process of finding the moment of inertia of the solid sphere involves integrating the moments of inertia of the infinitesimally small thin disks from the top of the sphere to the bottom of the sphere. You can see one of those disks within the drawing we have right here. We start as we normally do with the equation the moment of inertia is equal to the integral of r squared dm. But in this case we don't have r squared, but rather we have 1/2 y squared under the integral. This is the case because the moment of inertia of the disk is 1/2 y squared dm. And we're trying to add the moment of inertias of all the disks that make up the sphere to find the total moment of inertia of the sphere. So that's why we have 1/2 y squared instead of r squared under the integral. And next we know that we can't have dm under the integral because we can't really do anything with it. So we set up a proportion. We have the mass of the sphere over its volume, 4/3 pi r cubed, is equal to the mass of the disk dm over pi y squared dz, which is the volume of the disk. And this is the volume of the disk because pi y squared makes up the circle of the disk and dz is the thickness, so you get the volume if you multiply those together. So we have dm is equal to 3my squared dz over 4r cubed. Once we solve for dm, we can plug it back into the integral and we're left with the moment of inertia of the sphere is equal to the integral of 1/2 y squared times the quantity we just plugged in. We can pull out the constants and we're left with y to the 4th dz under the integral. We can also establish the bounds as negative r to r because we're trying to find the sum of all the moments of inertias of the disks. And if we work our way from the disks at the bottom of the sphere, negative r, to the top of the sphere, r, we're effectively finding all the disks. Now that we've established our bounds, we can go ahead and try to solve this integral. However, we notice that we can't really integrate y to the 4th with respect to z, so we have to find a way to represent y in terms of z. We do this by looking at the disks that make up the sphere and noticing that we can represent y squared as a function of r and z using the Pythagorean theorem. We see that y squared is equal to r squared minus z squared. Plugging that back into our integral, y to the 4th dz, we see that under the integral now is r squared minus z squared quantity squared dz. Now that we have this quantity squared under the integral, we can expand and we see that now finally under the integral we have r to the 4th minus 2r squared z squared plus z to the 4th dz. Once we have the polynomial in terms of z under the integral, we can go ahead and integrate. Once we take the integral, we see that we get r to the 4th z minus 2r squared z cubed over 3 plus z to the 5th over 5 evaluated from negative r to r. We can combine like terms, pull out a 2r to the 5th, and we're left with I, or the moment of inertia of the sphere, is equal to 3m over 8r cubed times 2r to the 5th times 1 minus 2/3 plus 1/5. Now it's just a matter of simplification as we can add the numbers in the quantity to the right hand side. We can cancel an 8r cubed from the denominator and we're left with 6/15 mr squared, which reduces down to 2/5 mr squared, and that's your final moment of inertia of the sphere.